Welcome to the H2S Corrosion channel. My name is احتشام زاده. An introduction to this channel is available on video number E28. Chapter 3, Section 4, Types of Corrosion. High temperature H2S corrosion. Our reference is Damage Mechanisms Affecting Fixed Equipment in the Refining Industry. API RP 571. 1. Description of damage. The presence of hydrogen in H2S containing hydrocarbon streams increases the severity of high-temperature sulfidation or sulfidic corrosion at temperatures above about 450 degrees Fahrenheit. Because of the smooth, large, relatively uniformly corroded surface produced by high-temperature H2S corrosion, it can lead to rupture-type failure rather than a localized or pinhole leak. This subject is covered in much greater detail in API 939C. This reaction is more destructive than traditional sulfidation due to the presence of hydrogen, leading to rapid material degradation and potential equipment failures. Understanding and mitigating this corrosion is crucial for maintaining the integrity and lifespan of equipment. 2. Affected materials. For the materials typically used in this service, the order of increasing resistance is carbon steel, low-alloy steels, 400 series stainless steels, and 300 series stainless steels. However, for practical, useful improvement over carbon steel, the alloy content of at least 9 chromium, 1 molybdenum weight % is normally needed. 3. Critical factors. A. The critical factors for high temperature H2S corrosion are the temperature, the presence of hydrogen, the concentration of partial pressure of H2S, the vapor-liquid ratio, and the chemical composition of the alloy. B. Depending on the quantity of hydrogen present, corrosion rates may be significantly different than those associated with high-temperature sulfidation in the absence of hydrogen. C. Sulfidation rates increase with increasing H2S content and especially increasing temperature. This figure shows the effect of temperature and H2S content on the corrosion rate of carbon steel. Increase in corrosion rate. Corrosion rate of carbon steel in H2S service in a naphtha desulfurizer from the modified Couper-Gorman curves. Generally, the corrosion rate initially increases with rising temperature, then decreases significantly, indicating a complex relationship. No corrosion zone at very high temperatures can be seen here. Initially, accelerating with rising temperature is due to increased reaction kinetics, but then decreasing as a more protective and compact corrosion product film forms on the steel's surface at higher temperatures, hindering further corrosion. Similarly, increasing H2S content initially boosts corrosion before potentially diminishing its effect. A very low H2S pressure can also increase corrosion, increasing corrosion rates by increasing H2S content. Vertical axis is the content of H2S and the horizontal axis is temperature. A very low H2S pressure can increase corrosion of carbon steel in a naphtha desulfurizer because it can alter the surface film's ability to provide protection and promote a sulfidation dominant corrosion process by creating a less oxidizing, more reducing environment that favors the formation of sulfide scales over protective oxide scales. High H2S partial pressure can sometimes reduce corrosion by promoting the formation of a more stable protective film. This suggests that optimal operating conditions need careful consideration to minimize corrosion, balancing temperature and H2S levels to protect the steel. D. Increasing chromium content of the alloy improves resistance. However, there is little improvement with increasing chromium content until about 7% to 9% chromium, as shown by the relative rate reduction factors in this table. Increasing the chromium content, decreasing the rate factor. The benefit of higher chromium levels is shown in this figure. This figure shows corrosion rate curves for chromium-containing alloys in H2S service. The vertical axis is corrosion rate and the horizontal axis is temperature. Carbon steel 5% chromium, 9% chromium, 11 to 13% chromium, 18.8 stainless steel. E. Chromium-containing nickel-based alloys have resistance similar to stainless steel. Similar levels of chromium provide similar corrosion resistance. F. Primarily, due to the higher partial pressure of H2S, corrosion rates in higher pressure units, for example, hydrocrackers and gas oil hydrotreaters, desulfurizers, are generally higher than those in lower pressure naphtha hydrotreaters. 4. Affected units or equipment. A. This form of corrosion occurs in piping and equipment in units where high temperature H2S streams are found, which is primarily hydroprocessing units, hydrotreaters, and hydrocrackers. B. Noticeable increases in corrosion rates may be found downstream of the hydrogen injection point, where the mechanism changes from sulfidation to high temperature H2S corrosion. The addition of hydrogen promotes cracking of the reactive sulfur species into H2S prior to the reactor, increasing the rate of corrosion in comparison to corrosion from the reactive sulfur alone. 5. Appearance or morphology of damage. A. Corrosion will appear as a uniform loss in thickness from the process site and is accompanied by the formation of an iron sulfide scale. B. Scale is about 5 times the volume of lost metal and may be in multiple layers. C. The tightly adherent shiny gray scale attached to the surface may be mistaken for unaffected metal. 6. Prevention mitigation. A. The corrosion damage is minimized by using alloys with sufficiently high chromium content. B. The 300 series stainless steels such as types 304 low carbon, 316 low carbon, 321 and 347 are highly resistant at typical service temperatures. C. Aluminum diffusion treatment is sometimes used to reduce corrosion rates and prolong the life of thin components such as 300 series stainless steel catalyst support screens in hydroprocessing reactors. D. Process simulations should be checked periodically to confirm that H2S levels have not significantly increased. 7. Inspection and monitoring. 1. Thinning in piping and tubing can be detected and measured using ultrasonic thickness measurement or radiography testing. Thinning in pressure vessels can be detected by internal visual testing and measured with ultrasonic testing. 2. Permanently mounted thickness monitoring sensors can be used. 3. Thinning in heater tubes can be detected using ultrasonic testing or by smart pigging. Smart pigging provides a more thorough examination and may find thinning missed by spot ultrasonic testing. 4. Actual operating temperatures should be verified and compared against design. Temperatures and sulfur levels should be monitored for increases above design. 5. Temperatures can be monitored using tube skin thermocouples and/or infrared thermography. 8. Related mechanisms. High temperature H2S corrosion mechanism is related to high temperature sulfidation in the absence of hydrogen. That is discussed in another video. Challenge number 53. Thank you for your time and attention. If you like to challenge yourself, please answer this question in the comments section. Increasing H2S content initially boosts corrosion before potentially diminishing its effect. A very low H2S pressure can also increase corrosion. Thus, this figure illustrates these claims.